Now we are doing the chemical properties of haloalkanes, and in the previous presentation I gave you all the possible nucleophilic substitution reactions of haloalkanes. As I told you earlier also that the incoming nucleophile should be a stronger nucleophile than the leaving halogen atom, and we did mention all the possible nucleophilic substitution reactions of haloalkanes. Today let's talk about the mechanism. How does this nucleophilic substitution reaction take place? Now, as far as the mechanism is concerned, these nucleophilic substitution reactions, they are of two types. You must have heard the names are so common. The first one is Sn2 mechanism. The substitution can take place by Sn2 mechanism, or it can take place by Sn1 mechanism. There is no specific order. I think मुझे आदत हो गई है पहले Sn2 लिखने की, then Sn1. We could very well actually first write Sn1 mechanism, then Sn2. कोई hard and fast rule नहीं है. But now that I have first written down the Sn1 mechanism, let's first talk about, Sn2 mechanism. Let's first talk about this Sn2 mechanism. Now this Sn2, the name stands for S is substitution, because that is the primary type of reactions we are talking about. There's a substitution of one nucleophile by another, and since there's a substitution of the nucleophile, N stands for nucleophile, and 2 because this mechanism is bimolecular. When we'll do the reactions, when we'll do an example, you will see that these reactions, they follow second order kinetics. If we speak about the kinetics of the reaction, you will see that these reactions in which substitution of a nucleophile takes place by Sn2 mechanism, they follow second order kinetics, thus the name Sn2 mechanism. Let's try to understand this Sn2 mechanism by an example first, and then we can talk about the important related points, right? So this is what we'll be talking about, and we'll take an example. We'll take the example of reaction between methyl chloride CH3Cl, which will react with OH negative, the incoming nucleophile, and what we'll get is CH3OH, which is actually written as, we'll do the mechanism, I'll give you all the details. It should be written like this, and Cl negative will be the outgoing nucleophile. Let's see how the whole reaction takes place. I'll open up methyl chloride so that we write carbon, then we write hydrogen atom, another hydrogen atom, third hydrogen atom, and this is Cl. Now since this bond is polar, this is delta positive, which is susceptible to the attack of the nucleophile, and our nucleophile, let's get a little colorful, is OH negative, right? Since this is negative, it will attack from the back side, right? It will attack from the back side because that is the site from where it is easy to attack on the electron deficient site, right? The next step we get is a transition state. What is this transition state? This is our carbon atom, this is one hydrogen, this is another hydrogen, this is another hydrogen. It is still linked to Cl, but at the same point of time it is simultaneously linked to OH also. There's a delta negative charge on this, there's a delta negative charge on this, and this state is called as the transition state, right? There's a difference between a transition state and an intermediate. I'll tell you what that difference is. Now we have the transition state, and after that this bond breaks, and the molecule that we get is actually like this. OH on this side now, and this is our carbon atom. It will have its hydrogen here, and hydrogen here, and our leaving nucleophile is Cl negative. This is the incoming nucleophile, and this is an outgoing nucleophile. So this is our nucleophilic substitution of halogen atom by OH negative atom, and the whole mechanism is called as Sn2 mechanism. Why? S because it is substitution, N it is a nucleophilic substitution, 2 because if we study the kinetics of the reaction, I'm going to rub all of this stuff from the board. If we study the kinetics of the reaction, it has been seen that rate of this reaction depends on both the concentration of CH3Cl methyl chloride as well as the concentration of OH negative. That is why we say that the reaction follows the second order kinetics. Thus the name Sn2 reaction, right? Now next point which you need to remember in this is that this transition state, as I said, it cannot be isolated, because if you look at the transition state, carbon is simultaneously linked to 5 different atoms, right? So it's an unstable state, it cannot be isolated. Transition state is highly unstable, because of which this is just one step. This is not 2 steps. The whole reaction, the whole substitution takes place in only one step. And since it takes place in only one step, Sn2 mechanism is known as the concerted mechanism. What does the word concerted stand for? It is a one-step mechanism. The whole reaction takes place in just one step, right? Next important point is, look at CH3Cl. We have Cl on the right hand side and we have this OH on the left hand side in the product. In methyl chloride, in the reactant, the nucleophile is on the right hand side, and in methanol, the product, OH is on the left hand side. So what happened during this whole mechanism is inversion of configuration. Very important to remember that in case of Sn2 mechanism, there is an inversion of configuration. From reactant to product, you will see an inversion of configuration, and this is called as Walden inversion. Right? We are talking about Sn2 mechanism. These are the important points about Sn2 mechanism. Now the next point is, if you speak of haloalkanes which undergo Sn2 mechanism, the order will be, the first one is methyl chloride, right? After that we have 1 degree halides, primary halides, जिनमें सिर्फ एक बल्कि ग्रुप होगा एक हाइड्रोजन की जगह. After that we'll have 2 degree halides, and after that secondary halides के बाद we have finally tertiary halides, right? So why is the order like this? The order is like this because the nucleophile has to attack from the back side. There should be the least possible steric hindrance here. The steric hindrance is minimum in methyl chloride. It's not just chloride, it can be any halide. In fact, I should write methyl halide only. It can be any of the halogen atoms. In a methyl halide, there are just 3 hydrogen atoms. There is no hindrance for this OH to attack on the electron deficient side. After that primary, we'll have 1 bulky group. After that secondary, we'll have 2 bulky groups. After that tertiary. Finally, सबसे कम probability of Sn2 mechanism है in tertiary halides, because उस वक्त there will be 3 bulky groups and there will be enough hindrance for this OH negative to attack on the electron deficient side. This, one more time, is Sn2 mechanism. Bimolecular nucleophilic substitution. It is a second order kinetics. The transition state is unstable. It is concerted mechanism. Whole thing happens in one step. There's an inversion of configuration known as Walden inversion. Then the order, very very important to remember. Sn2 ka order, methyl halide, greater probability than primary halide, greater probability than secondary halide, greater probability than tertiary halide. Right? We'll continue with the Sn1 mechanism in the next presentation.